Okay, so let us therefore now begin. Okay, try to, like we said in the previous module, that we're going to find out a relationship between boundary layer thickness, etc. Okay, let us first start by doing this. Okay, so this is basically what we're going to do is we're going to do a control volume analysis, okay, of the drag force on a flat plate which is being caused by the boundary layer, okay, because the flow is being retarded by the flat plate, right. So therefore, that is going to cause a drag on the plate, right. So let us see what that means. So what we're going to start doing is, let me draw a, so this is the flat plate, okay, this is my flat plate, all right, and then so this is x, okay, and you have, you know, flow coming in. So let me draw. So this is the flow coming in. So I would have okay, this is my velocity profile right at the entrance, okay, and we are going to look at this entire plate. So at the edge, at the outer edge, okay, at the other end, so this is my velocity profile, right. What you get at this side is this kind of a velocity profile, right. Now this, I am going to call this as u naught, and this is same as u infinity, if you will, okay. So this is it, right. And of course we have the boundary layer, okay. So we have a boundary layer. So say the boundary layer is something like this. Okay, right. So boundary layer is something like that. So essentially this, please don't get confused. So therefore, this here itself is also u naught. Okay, this velocity is also u naught. Okay, so meaning these two arrows. So now if I go even further up, these all will be u naught, same as this. Okay, all right. So this is my boundary layer. Now what I need, what I'm going to do here is I'm going to draw. I'm going to draw a control volume. Okay, so the way, okay, and the length of the plate is L. Okay, this is the length of the plate, which is L. Okay, now let us call this height, the height of the boundary layer at this edge, at the edge. Let's call that as delta. Okay, let's call that as delta, so that. And what we are going to do is we are going to draw a control volume in this way. So we are going to draw a tangent to the boundary layer at delta, and we are going to pull it down. That, okay. If we do that, then basically what here y is equal to delta, right, and this height is essentially h. I mean, we're just calling it that. So the y is equal to h. Okay, so if I do that, so I'm going to label this. So I'm going to call this as A, right? This bit as B, this as C, and this as D. Okay, so this is what we know, and again, okay, shear stress is not 0 here, and shear stress is 0 here. Now, what I did here essentially, you know, this one, this line, I am trying to draw a control volume here, which is ABCD. So this is nothing but a streamline. Okay. This line that I have drawn is nothing but a streamline which is which is moving, which is, so basically you do not have a flow across the streamline, you cannot have a flow across the streamline. Okay. Now, that is from your basic knowledge, maybe you should brush it up a little bit. Okay. Then what exactly is a streamline? So, the tangent to the streamline is going to give you the velocity, but there is no flow across the streamline. Okay. So, that is, so what the way I am drawing the trying to draw the control volume in such a way that it encompasses this part of the flow where the viscosity effects are present, right, which means in our case is existence of the boundary layer. So, I am cutting it off exactly there. So, I am using a streamline which best defines that. Okay. Now, once I do that, and please remember that this is like a square plate maybe. So, there the plate does have a width. So, as of now what we are assuming is that this picture does not change as we move along into the plane of the paper. Okay. So, therefore, this is my control volume A, B, C, D, right. This is my control volume. Now, similar to what we did the last time, let us find out the direction of the velocity. Okay. So, we have got inlet and outlet. Now, look at this wall here. So, look at this side, right, this side. So, here, okay, so A, okay, I am going to write the coordinates. I am going to write, okay, the coordinates of A are 0, 0 and B is 0, H. Right. So, this is essentially an inlet, 1D inlet, right, and here V dot n is what? Like we did yesterday. Okay. So, this is like a little area. So, the area vector. So, this is the area vector. So, this is minus u naught. This is from what we did yesterday, right. Okay. From a previous introductory class. Okay. Now, then we got B, C. Okay. Let us write down the coordinates. So, B again we have written. So, B is 0, H and C is L delta. Okay. Now, here is what? V dot n. Now, like I said, this has to be 0 because BC is a streamline, right. So, BC is a streamline and there is no flow across it. Okay. So, let me, I might as well write that here. BC is a streamline. No flow across it. Okay. Then again we have CD. Okay. So, C is here and the coordinates of D are L 0. Here V dot n is equal to this. Is that right? So, that will, so if I write that, so that is that. If I write u naught, it is not wrong, but then u naught is, it is variable if you see, it is not constant, isn't it? So, unlike at the entrance, okay, it is a constant velocity which is the free stream, in this case denoted by u naught, but on the exit C D here u naught is not wrong, but it is equal to u naught only at y is equal to delta at D. Okay. So, therefore, it is best, what we will do here is, it is best to write this as u, right, and that it is a function of y. Is that right? Okay. And then again we have finally dA. So, we got the coordinates here. Now, this again, right, the dA is again the streamline which is right above the flat plate. right above the flat plate. Well, again there is no flow across the streamline, but in any case here the velocity is 0 because it is near the flat plate, and that is due to the viscosity, right. So, dA is a streamline just above the plate. Okay. Now, so here too the velocity is 0. Now, of course, the fact that it is a streamline and there is no flow across it, that holds, but in this particular case, because it is a boundary layer and you are considering viscosity, and this streamline is right next to the flat plate, anyway the velocity is 0, velocity itself is 0, right. So, therefore, we have this. So, now what we are going to basically do? Now, this therefore, right, there is a certain retardation being caused due to the effect of viscosity on this boundary layer, and that is causing a drag force, right, which is what we are trying to consider and evaluate and put a quantity to it, quantitative analysis. And here, so we are going to sum up all these shear forces, right, which is going to cause the drag force, and the drag force is of course is in a direction opposite to the flow. So, we are going to write it like that. So, my drag force will be right, this is a unit vector in the direction of x, positive x, okay. And of course, pressure is uniform, pressure acts uniformly in all the surfaces. So, forces due to pressure is 0, okay, uniform pressure. So, therefore, let us try to sum this up, okay. Now, therefore, sigma Fx, right, which is equal to d. So, when I say Fx, I am talking about the total forces in the x direction, right, and that, like we said, is this, okay. So, what are we going to do here? How do we calculate force, right? In this particular case, force is given by rate of change of momentum, right, rate of change of momentum. This is something that we did in the review. So, try to go back to it. So, what we will do here is integrate. This is actually a surface integral. You could write a double integral there. I am not doing that. So, AB, okay. So, U V dot N dA into rho, okay. This AB, okay. AB, and so V dot N, as you can see, is 0 at BC and DA. So, all we have to do is AB and CD, right. This whole thing is AB and CD. So, these are the two, so entrance and exit. So, that is all we have to do. So, what we have here, so V dot N, right, into dA into rho is essentially the mass flux, right. That is the mass flux. So, mass into velocity, and this is the mass flux. So, rate of change of mass, right. So, mass into velocity, that is momentum. So, rate of change of momentum. So, therefore, this rate of change of momentum is equal to force. Okay. What I would urge you to do is write down the units and make sure that this boils down to the units of force. So, then both the sides will be same, right. So, let me just repeat that. So, this bit, this and this is mass flux, right, meaning it is mass per second, right, and this is m into u is what? Momentum, right, and this per second means rate of change of momentum. So, hence this thing is rate of change of momentum, which boils down to force. Okay. Rate of change of momentum is boils down to force. So, now let us write down. So, let us write this down. Let us write this down for, say, AB. Okay. So, for AB now rho is constant. So, we are going to take that out. we are going to write it for AB. So, AB, the surface goes from 0 to H. Okay. So, U, right, U is nothing but this thing, and V dot N we have already written, it is minus that, right. Area is nothing but area is nothing but B into dy, correct. So, B into dy. So, B is the width, right, width into the plane of your paper. Okay. This plus again rho, and this is going from 0 to delta. So, we are looking at CD. This bit is this one is for AB, and what we are doing here is for CD. So, CD we go from 0 to delta. U will remain as U, we can't do anything. Okay. And V dot N is nothing but Uy. Okay. And dA is again B into dy. Okay. So, that, so if I again, so if I do this, then what do I get? So, what I get here is minus rho u naught square b, right, y, so which is h, right. So, I am missing that step here, okay, plus rho b, okay, 0 to delta u square y dy. Okay. So, therefore, the drag force, okay, so I could write the drag force, okay, see it has a negative sign there, is nothing but rho u naught square b h minus rho b integral 0 to delta dy. Okay. So, if I do that, so this, let us call this as okay. So, we've got some expression for, we've got an expression for the drag here. Okay. So, if I do that, okay, if I do that, now from the mass conservation equation, right, from mass conservation equation, we know that rho control surface V dot n, okay, V dot n dA is equal to 0, right. This is from mass conservation. So, again we will go at the two boundaries. So, AB and CD. So, this if we apply to the boundary. So, what we get is 0. So, 0 to H, again this is for AB. Okay. So, minus V dot n is minus and B dy, right, plus rho 0 to H Uy, okay, into B dy. So, this is again for CD, right, and this whole thing is equal to 0. Okay. So, if we do the math here, so if I do the math here, okay, I'll not miss the step here. So, what we get is sorry. So, what we'll get is minus rho b u naught h, okay, plus rho b, oh sorry, this bit, this is not h, right, this is not h, this has to be delta, correct. So, 0 to delta u y dy, right, that is equal to 0. So, rho and b, right, so rho and b cancelled out. So, we can get that, okay. Therefore, h, okay. So, what we get here is h u naught is equal to 0 to delta uy dy, right. This is what we get here, and let me do this. So therefore, we needed an expression for this, right here. So h into u naught. So let's see if we will insert what we get there into this. Okay, we're going to insert, or rather use, okay, use 2 in 1. Okay. So if I do that, what we get is that drag is equal to b rho u naught. So I'm going to just replace h naught by this integral. So it is by delta uy dy minus rho b 0 to delta dy. Okay. So, or I will write d to be equal to b rho integral 0 to delta uy, okay, uy into u naught minus uy, okay, dy. So, right. So, we get this. Now, this, okay, so this was actually first proposed by Theodor von Karman in 1921, right. This was first proposed by him, and it's a momentum integral theory for boundary layers, right. It's a momentum integral theory. So basically, we use a control volume approach, and we we are doing an integral of the integral of the shear forces in order to get an expression for drag, right. So now, if you look at this, we should be able to find out this drag, provided we have some idea of the behavior of uy. So, if we knew uy, then we could easily get this. So, now the main thing is, how does the velocity, so what is the velocity profile, right. So, there we come down to that. So, various things have been proposed. So, for example, if we use this, if we use this approximate value. So, approximate, say we use this value, okay, this expression 2y by delta minus y squared by delta square. Okay. So, this is the expression for uy. So, this is between 0 and delta. Okay. So, if I use this for an expression for uy, and then we substitute it into this expression for drag given by the equation 3, then of course, I mean, I will let you do the math yourself. What I will give you some hints. So, what you should do is, you could take get another variable, call it eta, is equal to y by delta, right, y by delta. So, that at y is equal to 0, eta is equal to 0, at y is equal to delta, eta is equal to 1. Okay. So, therefore, what happens is, you could take, so therefore, the drag, okay. So, just replace it, okay. I am going to replace that. So, then you get all this b u naught square delta. The integral then becomes eta is equal to 0 to eta is equal to 1, and inside 2 eta minus eta square 1 minus 2 eta plus eta square d eta, right. If I do this and then finally this boils down to d is equal to 2 by 15 rho u naught square b of delta. Okay. And so what you see here is that for a given flat plate, right, if you know its width, if you know the free stream velocity which is coming in, if you know its density of fluid, it needn't be water, it could be anything else, air or anything else, honey, then this delta at a particular point, right. Now, this delta is the height of the boundary layer, right, the height of the boundary layer at a certain point, right, and then we can calculate drag. So, drag basically depends on the height of the boundary layer. It is very important to mention here that this delta will be different with x. So, as we move along x, delta is going to change, right. So, we kind of know that. So, let us call this that. Now, then, so therefore, this is from our expression here. Now, Kármán of course, is we are integrating the shear along the plate. Now, in our case, of course, the drag is essentially the shear stress which the fluid is exerting on the plate by means of its viscosity, right. So, let us say the shear stress is tau w, okay, tau w, and we multiply that by the area to give us the shear force. Okay. So, how do we do that? So, therefore, we write the drag. Okay. So, it is the wall, right, it depends on the x. Okay. So, b and d, b is the width. Okay. So, this is tau x. So, we integrate that over the length x. So, a certain length x, right, will be responsible if you sum up all the shear forces, the entire shear force which is exerted on the length x, because the shear stress will depend on the x, right. So, that should give us the drag, right. So, therefore, if I do that, so then I also, or I can write, or d, I will take the b out. So, b 0 to x tau w x dx. Okay. So, if I do that, so I am going to call this as 6, right. Now that I have that, so now from 6 I can write from 6 what I can get, right. This is what I get from 6. What I get from 6 is 1 by b. If I differentiate the drag force with respect to x, right, I get, this is yet another way of looking at it, right, that essentially the drag per unit x is equal, will give you the shear stress, drag force, right. The drag force divided by the area should give you the shear stress at the wall, right. So, this is what we get, and then what we will do is with this expression, right, with this expression we will insert this into 5, right. If we insert this into 5, what do we get? What we get then is this, that 1 by b dd dx, right, is equal to 2 by 15 rho u square, okay, dd x of delta x. Isn't that fine? So, we bring the b here, okay, and dx. So, we are basically differentiating this drag with respect to x. So, we get something like this, right. So, if I do that, and this is basically equal to tau w. So, therefore, this is equal to tau w, right. So, then this is my tau w, isn't it? This is by tau w. Now, there is something else also. Okay. Now, there is also, so therefore, now there is also the fact that tau w is equal to nu del u del y, that is from expression, right, and del u del y if I do it at y is equal to 0, right. So, shear stress is nothing but, which we did in the previous modules, shear stress. So, if I did not have say this, it is nothing but coefficient of viscosity into the gradient of the velocity. Now, shear stress at the wall is nothing but this gradient at y is equal to 0, right. So, what is that? So, therefore, in this case it is equal to 2 nu u naught by delta. Okay. So, we are going to box that up and say this is 8, right. So, 8, and this one, the previous one what we had done here, this one is 7, right. This is 7. So, now that we have an expression for tau wall, we are going to insert that into 7. Okay. So, this 8 is basically tau wall, which is, so this is the expression 2 nu u naught by delta. We are going to insert 8 into 7. So, if I am going to do that, so we insert 8 into 7. Okay. If I do that, okay, what we get, okay, is something like this: 15, okay, dx. I am going to leave you to, okay, and then I am going to integrate this. Okay. If I integrate on integration, so 15 nu by what is nu? This is nothing but this by rho. Okay. So, u naught, okay, dx, right, x is going from 0 to x is equal to delta goes from 0 to delta. So, delta d delta, right. So, if I do that, what I essentially get is delta by x, okay, is equal to 30 by u naught nu by x, okay, or essentially delta by x. It is very interesting, nu u naught x to the power half. Okay. Now, again okay. So, this is ultimately what we arrive. We started out calculating the drag force and so on and so forth. What you seem to have found out is that this x is basically the distance along the flat plate, right. So, now if you see, so if we do all this, then we get this, right. Now, this u naught x by nu, this is nothing but Reynolds number, and this is here Reynolds number, and when I say x, because Reynolds number is basically what? The expression for Reynolds number is rho v d by mu. This is what you know, right? This is nothing but Vd by nu. Okay. So, now this d is the distance. Now, this distance in this case is along x, which is the distance which is in the direction of the movement of the fluid, right. So, therefore, this x, the x is important because there is also a displacement in the y direction. It is not Re y, the direction is y. So, this is not Re into x, this is Re subscript x denoting that this. So, therefore, what you see is that if you move a certain distance x, so delta can be found, you can find out the height of the boundary layer for a certain delta. So, delta by x is around 5.5 by Rex. Okay. So, these are the accelerated formulas. Then of course, I am not getting into more issues now, laminar, turbulent and all of that. So, therefore, now for the problem that we had set up, right, that for a given plate, okay, what is the distance at which the height of the boundary layer is 1 inch. So, I think you have sufficient information here to solve that problem. Okay. So, what I will do is I will go ahead and stop here and meet you again for the next lecture, and let me not give you the answer to the problem. You do it and then do this and do this yourself and then come back and check it. Okay. So, I think you have enough sufficient information available here to find out that. Okay. So, I think we will stop here and pick it up next time. Okay. Thank you.